So anyways, this project began with a fascination with how socioeconomic variables tend to sort of reproduce the same patterns across space, particularly those associated with social maladies, a sort of spatial collinearity. I wanted to create a method for distinguishing cartographically subtle variations to make exploratory analysis more effective, compared to, say, just throwing a bunch of variables on a map. The technique I'm going to use here is geographically weighted regression with lasso and ridge variance, a method that is a lot like, as I tried to depict here, moving a magnifying glass around a map and modeling as you go. But first, I wanted to motivate the problem. The origins of this come from a hackathon that was held at UCL CASA last year, where myself and others were charged with making policy recommendations for how to ameliorate the effects of an aging society. Obviously, aging societies come with a lot of costs. Chronic diseases drain public coffers and cost individuals. And so the challenge here is to move from a sort of aging society to a longevity dividend, as it's sometimes called in economics, where a population is healthy and spry, so elderly people can participate more readily in the national economic output and also just like the social fabric. So on the left side so we're going to set up a regression here, and on the left side of it, we're going to set up healthy life expectancy, which is collated by the Office of National Statistics. And you can see that it's pretty closely related to life expectancy at birth, but not perfectly, and that it has some distinct spatial patterning to it. And so we're going to try to get to the bottom through geographically weighted regression of how of what is influencing that spatial patterning. On the right hand of the regression, we're going to take basically a suite of socioeconomic conditions and then a set of environmental factors. The economic conditions are things like income and unemployment. I have several different vintages of income here because I wanted to test, things like maybe a bygone era effect. And then there are about 13 other environmental factors collated by the CDRC at UCL. So other ones include dentists, betting shops, and what you see here. For the beginning, I wanted to just do a dive into the clusters of where health span and lifespan diverge. So because it's lifespan minus health span, a high value is bad and a low value is good. And we see distinct clusters arise around London and particularly in the north. And you can test the sensitivity of these clusters by varying the p-values using local indicators of spatial autocorrelation. You can adjust the p-values, and at variables of statistical significance, you see different size clusters, but most of the cores remain constant over time. Now, to actually model this problem, I wanted to use geographically weighted regression, which is a form of linear regression that adjusts across space. These two animations should kind of give the gist. Rather than estimating on the entire data set as you would in a typical linear model, we're going to move a window of observation across all spatial units, fitting a model for a given bandwidth around each focal observation. Because of this, geographically weighted regression requires an additional specification. It requires a bandwidth and a kernel. The bandwidth is sort of the size of that window, and the kernel is the decay function, so how much you're going to penalize observations for how far away they are. The primary benefit here is that by downweighting distant observations and upweighting near observations, leveraging Tobler's law, we can estimate a model that is sensitive to spatial heterogeneities, as we just heard briefly mentioned in the last talk. But one issue with geographically weighted regression is that as you trim your data, the ratio of features to observations becomes problematic. There's a sort of P to N problem. Because of this, we're going to add another term, lambda, which manages collinearity and dimensionality. And I wanted to test the sort of values of a ridge penalty versus a lasso penalty. This tuning parameter takes on different forms shown here depending on if we use ridge or lasso regression. Both are shrinkage methods which reduce variance at the expense of bias, but the ridge penalty pushes variables approximately to 0. On the x-axis here, you have the lambda coefficients, you have the lambda values, and on the y-axis, you have the betas, and each line is a variable. So it's going to sort of asymptotically approach 0, whereas the lasso penalty is much more comfortable pushing coefficients all the way to 0, and that's useful because if you have a constrained window, so here we only have about 24 observations per model, you want to reduce the dimensionality of your model by figuring out what is actually contributing to it and what is not. To test which one was better, I just ran cross validations, and the lasso comes out on top in terms of root mean square percent error. Interestingly enough, the residuals actually, when you map them, look a little worse for the lasso, but that's because of a couple outliers, which the lasso doesn't seem to be managing very well, whereas the ridge regression seems to have an issue with some sort of patterning, not necessarily heteroscedasticity, but there's something going on there. So from here, we move on with the lasso rather than the ridge. To specify the model, I wanted to build on David Wheeler's work on geographically weighted lasso. He has an R package called GWRR, and it has ridge and lasso variants, but he does it all sort of inside a black box. And so I wanted to, and within that, each model is specified uniquely. So you keep you keep different terms based on the lambdas across space. Here I opt for a version where we calculate the average variable importance by running a variant of Wheeler's GWL. The process is roughly such: we're going to iterate through, and at each observation, we're going to run k-fold cross-validation and store the lambda with the best prediction accuracy. Prediction accuracy is pretty valuable here because with a constrained sample size, I don't really want to get into p-values personally. And those lambdas are mapped here. And then we're going to store those and store all the coefficients for each model, and then take the absolute value of the mean coefficient across iterations. And those are plotted here, and you can sort of create a cutoff. Maybe if this was like a scree plot, you'd take the elbow, where you're only going to accept variables above that. From here, we can run a series of bivariate geographically weighted regressions just to see what kind of patterns evince themselves. So here we take income and unemployment. Both are negative. So as income and unemployment increase, healthy life expectancy decreases. This is sort of counterintuitive for income, although it's intuitively attractive for unemployment. What's interesting is that there's a much stronger coefficient in the south around London, suggesting that maybe there's something going on with the sort of pricey and wealthy area. Particularly, you can imagine a high unemployment rate in an otherwise pricey area would be problematic. Then we can check out some of the environmental determinants that I mentioned earlier. Care facilities is sort of an index that I created using dentists, doctors, hospitals, and that is much more distinctly urban than what we saw on the last slide, as are lifestyle factors, which include things like betting shops, pubs, those kinds of things. As distance to those things increase, healthy life expectancy increases as well. The interesting thing here is that it seems to hint at a sort of urban penalty where we're just sort of capturing something about cities, but none of these variables are actually contributing to it, because it's hard to think of the mechanism by which these variables would be influencing healthy life expectancy in a positive direction. You wouldn't want to be far away from doctors if it wasn't just far away from density or something else. So we can layer all these coefficients. This is actually just a sort of Macargian layer. I I got my start in architecture, so Ian McHarg was a big contributor there. And there's no real math behind it, just normalizing everything and layering them up with an opacity. And London, again, is implicated. When we group by region, we can see that the mean effect size in London is higher than anywhere else, although some areas have more variance and certain variables that stick out. But across the board, London shows a stronger effect size for all variables tested, suggesting that there's something going on and there's some kind of urban problem around healthy life expectancy. We also tested air pollution, but that actually wasn't very significant, so it got dropped from the model. So whatever is causing this urban penalty, it's likely not air pollution. So these are the sort of takeaways. The wealthiest urban centers have problems with lifespan and health span across the board. Indicators of urbanity and longevity point in opposite directions, but with spatial variations. So we can see that you often see stronger effect sizes in the around the major cities in England. But the final thing is that in a lot of cases in geographically weighted regression, so I hope this is a takeaway for people here, is to choose lasso over ridge, and also to definitely choose one of these two tools for managing collinearity and dimensionality. The lasso has better prediction and aids in model selection, whereas the ridge, if you had a sort of a priori assumption about your model that you wanted to keep in it, it preserves the coefficients, and it has a sort of attractive bias variance trade-off. Because it will be less biased given how little the penalty is. I wanted to finish with some acknowledgements. This obviously came out of the hackathon that I mentioned, so thanks to everybody there. And this wouldn't have been possible without a whole suite of R packages. I can now take any questions. I hope that was fast since we were falling behind.
That was perfect timing, Andrew. Thank you very much.
All right.
So we do have time for some questions, please. So type into the chat if anyone's got anything they'd like to ask. You just answered my question in the final slide there, Andrew, which was going to be the kind of software environment that you were implementing this. So everything was done exclusively in R there, was it?
Yeah, I basically took a series of R packages and sort of ripped them open to make the machine learning a little more accessible. So I was building on some other work, yeah.
Yeah. Why did you just restrict yourself to England? Why not do Britain?
That was actually where the CDRC data came from. I really was interested in environmental determinants, and I couldn't find a good data set for things. I could have created one whole cloth, maybe using something like OpenStreetMap, but looking for those spatial variables like hospitals, dentists, doctors, I wanted to probe that, and the only data set I could find was England only. That was sort of sad, especially given that, as I said, you want as many spatial units as possible to help with statistical power.
Yeah, interesting. Need more questions, audience. Come on, we've got a lot of people sitting and listening and not asking very much here. Okay, we've just had a question in from Martin Charlton, who asks, did you think about mapping the condition numbers? Then you'd see where collinearity is an issue.
I did not actually think about mapping that, honestly. So that's actually a good pointer if I'm going to build on this. But yeah, so that's actually a good question. I did not.
Another question from Sarah Wise. It looks as if you controlled for sex. Were there other demographic categories, e.g. ethnicity, which you considered?
I could not actually get data for anything other than gender, sadly. That would probably be a pretty important factor in this urban patterning, but I couldn't get data on that.
Where next, Andrew? Where are you taking this? Was this just a one-off, or is this part of a program heading in a direction?
I'd love to sort of build on this model to find some means of causal inference. Right now, it's purely exploratory. I'm sure everybody here can recognize that, and that's kind of I mean, that's just not as satisfying a field of academic inquiry. So there are some other things that I'm keeping my eye on. There's some Bayesian techniques like sparse Bayesian networks, but I'm struggling with causal inference.